Hello, it's Keith here, and this is the third in the Chibiakumas series of my programming tutorials. Now, the last two lessons we've been having a look at various parts of the Chibiakumas source code and how to change them a little bit. We're going to be continuing that, but in a slightly different direction this week. We're going to actually look at how to create sprites for Chibiakumas, and we're going to start looking at that. Now, sprites in Chibiakumas episode 1 and 2 before version 1.666 were actually drawn with Krita, and then they were converted to bitmaps in the correct format via an assembly language program within the Amstrad CPC itself. What I was using is a screen converter to convert the sprites and then binary converting those into the data file format using ASM code. It was a bit clunky and it took a lot of time when it came to making changes to individual sprites, because I'd have to convert the sprites to a bitmap, save the bitmap as a SCR file, import it into the disk, and then get the ASM code to convert that to a binary file, and then put that binary file on the disk. So it was a bit inconvenient, and more beyond that, I wanted to be able to convert the same sprite files for different platforms with different limitations, because of course the Amstrad CPC is basically 4-color in my games, the MSX is 16-color, and the Spectrum is essentially a black and white system with color attributes. So this was going to pose a big problem for me, and so what I decided to do is write my own Sprite Editor to do the conversion work for me and hopefully save me some time, and that's what you're looking at here. Now, my Sprite Editor is written in Visual Studio 2008. I use a free copy of it. It's the Express copy I use, and the source code for this is free, so you're welcome to download it. I should point out, however, I'm not a professional C# programmer. I did this as a hobby, so it's not well commented, and I'm sure I've made loads of horrendous design mistakes that people will complain about, but it's free, so they can just shut up. So anyway, so let's have a quick look at the program and we'll describe a little bit of how it works, and then I'm actually going to draw a sprite today and you can see it in use. So you can see here there's 3 copies of the program, and one is showing CPC sprites with their 4-color. We've got an MSX sprite here which is 16-color, and we've got a Spectrum sprite with color attributes here. Now, at its heart, the AkuSprite Sprite Editor is a 16-color system, and I can show you what I mean by that. If I turn this back to MSX viewing mode here, and then go back here, you can see that this actually is a 16-color sprite, but then when I change to Spectrum mode, the colors are ignored and it's converted to a black and white sprite, and then the color attributes are applied to the top. And you can see the color attribute options here depending on the system. So this is Spectrum. This is Commodore 64, and you can see the resolution is halved because in 4-color mode the Commodore 64 is lower resolution. That isn't currently functional. That's going to be the Nintendo NES. That's going to be the MSX 1. That again is also not functional. A lot of this is coming soon, and this is the Apple II. The Apple II is half resolution again, and it's a 4-color system that has one of 2 strange color palettes. So a lot of this is work in progress. Some of it's working, some of it isn't. Basically, the AkuSprite Editor is in constant beta. I add features to it as I need them, so hopefully everything in it works. Some things don't work, but I'm planning to make them work. And whatever you download, if you're watching this 5 years in the future, is bound to be different to what you're seeing here, because it will have had more features added to it. So anyway, so as I say, it's essentially a 16-color sprite editor with color attributes. There is a 17th transparent color. You can use this, and what happens is when you save it to a binary format, it will either be converted to color 0, or if you're using one of the special formats like the sprites on the CPC, the transparent color is a special combination of bytes. It essentially looks like a rainbow. So pixel 1 would be this, pixel 2 would be this, pixel 3, pixel 4. And a byte with that combination is converted to transparency within the code. So the transparent color is never saved to a binary format as a 17th color. It's converted to whatever is capable, if anything is capable, as a transparent color within that system. As you just briefly saw, you have display modes here, and these don't convert the byte data that's held in the sprite. It's just for viewing and also for exporting. So if you export in dither mode here, you'll see dither mode converts half colors, then it will actually save that in as the 2-color format. But if you saved as regular mode here, then you would save this instead. So it's not just for viewing, it's for exporting, but it's not converting the stored data. Now, when you're saving and loading the sprites themselves in native format, they're actually saved as TXT files. And the reason for this is simple. I will just open one. They're actually a text file. I know that's very strange. There's a simple reason for that. I find I find using things like XML quite difficult. I've written CSV viewing code in MS-DOS that supported Japanese Unicode. I'm very confident with CSV, and it doesn't matter what system I'm working on, I can write a CSV parser for it. I don't fancy writing an XML parser on an Amstrad CPC, but I could easily do that for CSV. That's the reason for my choice. And it does have some benefits. You can even open this in Excel if you want to start messing with the byte data, and you can actually kind of look at that, and you can even see that is the Yume character there. You can tell just by looking at the data. So as I say, I'm quite happy with my CSV choice there, but I know some people will find that very strange. But it does give you the benefit that if you want to quickly copy half the sprites out of one file and paste them into another, it's as easy as opening it in Notepad. So there we go. So you want to use these text files for your main sprites and then export to the destination formats, because while there are exports for a lot of formats, there are not importers, so you must save as basic text file sprites. So here you've got your editor window. I'll just find the sprite I'm going to be editing today so I don't wreck something important. So you can see here we can draw, and if we were working in a 16 color mode, we can select our color in the top pane here and draw in that color. Now we can change our colors by just enabling this. We can click on a color and we can select our palette option there. I won't, because I don't want to ruin my palette. Or we can change to this hash mode, and then we can enter a color in the same format as the tutorials we use. So for example, white would be this. That's one nibble per color channel. Or we could do red like that, and so on and so forth. So I have obviously not programmed in the cancel option there, so we'd better reload that. As I already said, this is a sort of constant beta. There's going to be bugs, and as soon as I find them, I will fix them. But anyway, so we can set our palettes. We can, as I showed already, we can view different alternate palettes as they're called, for the systems that have color attributes, basically. So where it's a 4-color system with color attributes like the NES or something like that. The starting point is always working in 16 colors, designing a sprite, even if you're only using colors 0 and 1, and then applying the attributes later. We've got various drawing options. We've got pixel paint, which is the basic option, so we can draw pixels like this. We have a check mode, which allows us to do a kind of dithered pattern, and so as you can see, this is now skipping every other pixel. So we've got various options there. We have ZX paint, which is where we apply our color attributes. So if I wanted to apply spectrum color attributes to this, I can select a foreground color and a background color and a brightness option here, and you can see you've got a little preview of it here, and I can click this to flip those around. And then here I can either paint normal, which is essentially the same as pixel paint. I can apply colors, in which case I'm just filling the background, or if I select pixel map, I'm now only affecting the foreground. In normal painting mode, I'm affecting both, you see. So that's the ZX paint is a kind of special version of pixel paint, which only affects the black and white data, only affects the color attributes, or affects both. Now, color swap is also really designed for the Spectrum. If I just change the view here, I will just change it back to 16 color mode. So in some cases, you need to simplify your colors. If I just zoom in on this sprite here so we can see it a little bit better. So for example, I might need to make these mouths black, color 0, to make it work better on the Spectrum. And so what we can do here is we can select this to sprite. So we're going to change the color of the sprite. I select the color that's the destination, and then I click on the color I want to swap. And now you can see all of the grey pixels have changed to color 0. Now alternatively, I can change this to block, and this works within an 8x8 grid. So now if I click on this, you'll see that that black border disappeared, but this black border is still here, and now it's disappeared as well. So it's essentially a way of changing a few pixels within a sprite within those 8x8 grids. Now, there aren't any more advanced functions like fill or maybe pattern drawing or object drawing. What I would suggest, if you're not happy with the functionality within this program, and that's not in any way suggesting you should be, you can go to the edit menu here, do a copy to clipboard, then you can load up the sprite editor of your choice, and I always use Krita because it's free. And now you can see we've got our sprite here. I've got a palette at the bottom here. I can, as long as I use the correct colors, I can do something here, like let's draw this, what's left of this guy's mouth in here, and let's maybe repair his body a little bit. So there we go, we've fixed him somewhat. Copy it back to the clipboard with Control-C, edit, paste from clipboard, and now the sprite has been copied in the exact same format. So this sprite editor is really just designed for basic touching up and applying color attributes. You can't apply the color attributes using that copy paste function, but it's a good way of doing simple stuff where you need to just correct the odd pixel, swap the odd pixel, fix up the spectrum color maps and things. But as I say, copy paste to the clipboard if you want to edit in more detail. And there is a new feature as well where you can do this save bitmap map function. So we can actually export all the sprites as bitmaps. All we do is we go to here, select save bitmap map. We'll go to my desktop here and we will call them just T for temp. It's taking a while because it's got a lot of work to do here. And what it does is it saves every single one of the sprites and a map which defines the location of those sprites within the bitmaps. And if I cycle through them, you can see this is the position of the sprites defined by colors, and it's off the screen unfortunately, but if I just resize things. So at the bottom of the screen here, these are the colors that I use to define the sprite numbers. So each of these is 10 pixels wide. So this one is color sprite 0 and the correct color for that sprite, and this will be Sprite 64, I think. But essentially each of these sprites is a separate color. It has to match the correct color map, because when it loads back in, it says, right, what area is covered by Sprite 7's color, for example, and then it says, right, well, this is the area that is Sprite 7, and then it looks at the other files and says, right, well, this is going to be Sprite 7's first bank, and this is going to be the second bank, and that's something I've actually missed out here. So the Sprite Editor can support up to 63 sprites, and you can browse through them using Lick Sprite and Last Sprite, but it can also support up to 8 frames of animation. So I can do next bank and last bank to toggle between them. Now, Chibiakumas only supports up to 4 banks, and the game I'm developing at the moment only uses 2 of them. But in theory, you know, I've put a bit of future-proofing in for 8 banks, and it'd be perfectly possible to do 16. It's just honestly, I'm not that good an artist. I'm not going to manage 16 frames of animation on a single sprite. So saving some memory there by just limiting myself to 8. But anyway, again, you can edit these files in whatever you want, and Bank 0, well, all of the banks have the color palette here, but when you load these files back in, which you can do with this load bitmap option, the sprite data is re-read in using these colors from Bank 0. So if you change the colors here, you can use whatever colors you want in here, and it will reset the palette in here. Effectively, I can create a new, if I just do file, I'll just open a new copy of the Sprite Editor. So here is a blank copy of the Sprite Editor. We've got no color palette or anything. And then if I just do file, load bitmap, and if I just select one of those files that I just saved, you can see the color palette is back because that's been read in from Bank 0, and all of the sprites are back again. And not just one bank, but both banks. As I say, even though the color palette for reference appears on all of the sprites, but when it loads back in, it's got to be the same palette for all the banks. So it's only loaded in from Bank 0. So that's just something to note there. So we've got various options here. We've got pixel paint options here, ZX paint options here. We've got some settings relating to the sprite. Well, byte aligned is to do with the binary export formats. In some cases, you need a sprite to start on a 256 byte boundary so that you can do things within the code. This is especially true with the scrolling tiles. The tile maps need to be byte aligned in some cases because the code relies on it. So you can force one to be byte aligned even if it wouldn't normally be within the exported memory. You've got fixed size. Now, the Chibiakumas sprite engine will skip pixels from the top and the bottom of a sprite if they are blank. In some cases that's a problem, especially on the ZX Spectrum. So what you can do is you can tick the fixed size option, and then it will say, hey, what size do you want it to be? Now this was going to be 32 pixels wide and 31 pixels tall because that bottom line is blank. Now if I need this to be square, I can change it to 32, and now it will not try and recalibrate that sprite size. It will force it to be 32 by 32, and you can see that here. So the used area is 0,0 to 32,32. The vertical position is to do with when you export to MSX formats, it's saved as a giant tile map, and sometimes the vertical position is used by my code. So there's 26 sprites, and this is sprite number 26, and there are 28 in use in total. As I say, the sprites are numbered 0 to 63 in the code as it currently stands. So we can browse around here. We've got a preview at 0 zoom here. We can zoom in and out here, And we've got some more options here. We've got the settings page for advanced settings. There is an option to import Chibiakumas format files from the Amstrad CPC. If there's a header, you need to have this ticked. If there isn't, you need to untick it. That's an AMS-DOS header, that is, not a Sprite Editor header, because they always have a Sprite Editor header. By default, you can edit 256 pixel size sprites. You can turn it up to 512 if you're doing CPC screens, because they're 320 by 200. It uses a lot more memory, and it was crashing my Windows XP virtual machine at one point, though at the moment it seems okay, but by default it's 256 because it's very few machines, only like the C64, the Amstrad CPC and the X68 that are going to need that bigger size. You've got frame overlays. Now these are these are a feature that shows a semi-transparent version of the other bank. So if you're working on frame 2 and you want a reference view of frame 1, you can enable it. So we can turn that on and off here. You also have, we'll just turn that to none. You've also got the grid. We can turn the grid off if we want to. We can have an 8x8 grid, which is the normal one. We can make it bigger if we prefer that. So the top size is 32. Usually it's 24. In general terms, Chibiakumas uses 24 pixel wide and 24 pixel tall sprites. That was a limitation of the first version of the game. It's no longer a limitation, but it generally sticks around. Now this option here is for the Apple. The Apple uses 7 pixel wide tiles essentially. The font is 7 pixels wide. It's very strange. So that's designed for that system. And if the grid's annoying you, just turn it off. If you want it but it's too bold, you can turn off the high visible grid. And if you're trying to fix spectrum attributes, you can turn on the dot grid. Now this was because some areas of some sprites were black, but even if the sprite's pixel data is black, the color attributes will need to be set in case anything that's not setting its own, like bullets in Chibiakumas, are going to be some color. Because I was having areas of the sprite that had background attributes of completely black, and the bullets were disappearing. Well, that's not good. So this was to allow me to test the sprite and just check there were no completely black areas. So that was what that was designed for. You've got a dither option here because there's 2 dithering options for the Amstrad CPC mode. There's a sort of more bold version, and depending on what you're converting from 16 to 4 colors, one might be better than the other. If you want to permanently apply that instead of it just being a view, then you can go to the view menu and select apply view color conversion. So if I do that now, and then I go back to view and 16 color mode, you can see it's now converted it to a black and white sprite. So that's how you can, if maybe you want one sprite to be using the alternate mode and one sprite to be the normal mode, at the moment the only option for you there is to actually fix those conversions into the sprites. That's another important thing I should point out. While this does support ZX and C64 attributes, and it's going to support more in the future, it can only support one set of attributes in a single text file, and that's a memory limitation. I don't want to store 20 odd versions of the color attributes on a file, because for all I know the file could be an MSX file anyway. So for simplicity, I'm only saving one set of color attributes. So you need to save different versions of the files if you're using multiple color attributes. And you can actually import the color attributes separately to the pixel data. So if you've redrawn your sprite's pixel data, but you want to import the color attributes from the old version, you can always do that. That was intentionally to sort of get around that limitation, because really, in most cases, while the sprites are converted from the CPC to the MSX or vice versa, and tweaked for the ZX Spectrum, there's always cases where they aren't quite the same files. So I tend to copy and paste them between the versions. As you saw at the start, I had 3 versions open, rather than actually having one version that does all 3 jobs, because it just doesn't really make sense to try and do that. So yes, we've got lots of options here, and of course we have exporting options. We also have the copying options. We've got canvas size options. We can duplicate bits of the sprites. They're not very good functions. As I said, copy and paste to try to if you're trying to do clever things. But we do have flipping. We can shift the sprites around, and we have a tiling option. On the Amstrad CPC, the tiles are 32 pixels wide. On the Spectrum, they're 64 pixels wide, and on the MSX, they're 256 pixels wide. And the tiling options here and here are to allow that to be done quite easily. You can also tint the palette. This was used for the dark caves level of Chibiakumas. I just made an extra function onto the code that would allow me to tint the palette 20% red or something. So this is the beauty of having your own sprite editor. You suddenly wake up with some quirky idea, you just program it into the code, and C# is very fast for just plugging things into the code. So what can we export to? Well, the answer is an awful lot. We can save ASM code that will be the palette, and it says here, mostly off screen, copy to clipboard. Well, now if we get in a notepad, well, we can now paste in the assembly code for my tutorial series that will define the palette that you've got shown above. So we've got that option there. But we've got far more exciting things than that. We've got Sprite Compilers. The Sprite Compiler is the thing that does the backgrounds in the last boss of Chibiakumas. And what it is a full screen sprite that is assembly code that will draw that sprite. So we can save the current sprite as an extra object. And you can have multiple ones in a single bank, which is why you've got add one, clear. Clear will clear all of the current ones, add one to all, and add an extra one to the current assembly code. Add one diff will add the difference from the last one to the current sprite, so you can have lots of frames, but only saving the difference. It's quite complex. I am going to cover it in my tutorials because I think it's quite interesting, but that's all I'm going to talk about today. But that's only the start of what we have for the CPC. We also have loading binaries from the Chibiakumas game. We should be able to load them. Saving CPC plus binaries. Loading regular, that was CPC plus, sorry. Loading regular binaries in the Chibiakumas format. Saving binaries in the Chibiakumas format. We'll look at that in a second. Raw bitmaps. Now these are the ones in my tutorials. They're literally just byte data as it appears on the screen. So you've got to write your own viewer for that, or sprite viewer, but it's not complex because all you're really doing is dumping the bytes to the screen and looping and repositioning the writing position as you go to the next line. And that raw bitmap format exists for all of the systems that I'm supporting, and you'll see in a second there's a lot. Zigtile is an experimental format for I'm thinking of doing a platformer game sometime in the future. I've created a tile map function for the Amstrad CPC, and it basically alternates the direction. So the first direction goes left to right, first line goes left to right, second one right to left, and that was to optimize the code that was showing the sprite because that's the way it was moving down the screen in memory. You can save CPC screens, and you can save RLE assembly files, and again that says copy to clipboard. So let's have a look at what's in that clipboard. Well, what is this? Well, what it is, oh dear. Usually another bug there. Usually I only do this with a single file. What it actually does is it's included the decoder multiple times, so that wouldn't work. Again, another bug I need to look at. But essentially, what this is a run length encoded binary data in a format that you can just execute within your ASM code, and this is used by the introductions of Chibiakumas. It's used all over the place, to be honest. Like the game over screen, anything you sometimes can see them kind of drawing a little bit slowly. That's because they're run length encoded, but it's quite an efficient format. You'll save usually 50% or more, especially if you're willing to work and design around the run length encoding optimization. So that's a format I wrote, and that exists on the CPC. Now on the MSX, we have some options as well. We can save raw bitmaps again from the tutorial series, the palette, which is just the same format. We can save MSX RLE, which is again just a full screen RLE. There is a special decoder, and the MSX decoder is clever because rather than working from memory, it actually works direct from disk, streaming straight into the VDP RAM. It means it's quite big, but it means you don't need any temporary memory because the MSX screen is 24 kilobytes. So even with 50% saving on the size of and that's if the RLE encoder is working well, that's still 12 kilobytes of memory on a 64 kilobyte system, and it's not really viable. So I stream straight from the disk on the MSX. And we've also got MSX RLE sprites. The binary sprites on the Amstrad CPC and Spectrum don't work well on the MSX for the same reason as I've just described. The normal systems, as we'll see in a second, have the binary data of the sprites after the header, which defines the size and things. But on the MSX, the sprites have to be within the VDP memory, not the Z80 memory, and so they're saved as a separate file, and that file is RLE encoded because basically it's more efficient than that. I think it's actually faster to load an RLE from the disk than a non-RLE because the process is faster than the disk. So I RLE all of the sprites on the MSX. So, well, what else we also have the ZX Spectrum. We have some special tools for the ZX Spectrum. We have the Sprite Compiler again for the end sequence. It's not possible to do compiled sprites on the MSX because the VDP memory is too slow. So we have a couple of tools relating to the special ZX Spectrum's limitations. We have the ability to load a Spectrum screen, save binary sprites very similar format to the Amstrad CPC. The only difference is they have color attributes saved after the binary data. Save spectrum tiles. These are the same as binary sprites, they just have no color information. This is used for the background mountains and things because they're actually the color attributes for those are set differently. They're not set as part of drawing the sprites themselves. Saving a bitmap spectrum font, and this is actually used for the other systems as well in my tutorials because I'm using a 2-bit font for all of my systems at the moment in the tutorials. Save a spectrum screen, well, that should be self-explanatory, with color attributes of course. Save a raw bitmap, that's for the tutorials. That doesn't save color attributes. And RLE ASM color, well, that's just again a assembly language piece of code that will recreate the sprite on screen with color attributes. Doesn't have to be a full screen either, but generally it's a large object because if it's very small, there's no point using RLE. Now these are the main systems, but we do have more. And one I should point out, Enterprise and CPC are the same thing as far as my programs are concerned. I use the exact same sprite data on the Enterprise and the CPC. So we've got Game Boy, save raw bitmap, Atari 83, save raw bitmap. These are for the tutorials. Sam Coupe, save raw bitmap. Save binary sprites, because while Chibiakumas doesn't exist on the Sam Coupe, I have ported the sprite viewing code. So, and this was because I'm planning to do games for the Sam Coupe in the future. However, at one point I was thinking my next game would support all the previous systems and the Sam Coupe. Unfortunately, I've decided to put that back quite a lot. What I'm now doing is I'm trying to write a game based on the Grime Z80 source code that will support around 20 systems on the 6502, the Z80 and the 68000. It's going to be much more advanced than Grime Z80, but much less advanced than Chibiakumas. And my hope is that at some point in the future, I will be sufficiently proficient at programming all of those systems to be able to write my sequel to Chibiakumas on probably nearly 24 systems rather than just on 5. So holding things back and waiting to get some more experience and some more source code, honestly, that I've written and understand, should allow me to make it a very decent game for a very large number of systems, whereas if I did it immediately, it would only be for 5 Z80 based systems. So yeah, there is some Sam Coupe functionality, but it's not used by anything, nor is it honestly going to be for foreseeable future. Now, the Elan Enterprise, it's almost the exact same code, but the RLE ASM has some very slight tweaks for the Enterprise. It uses a different version of the RLE decoder. That's basically it, I think. So the actual bitmap data is the same because the Elan Enterprise mimics the Amstrad CPC screen layout. And the master system in the Game Gear, raw bitmap. And then the 6502, you got raw bitmap options 2 and 4 color for the Atari, and all of these just have raw bitmap because these are systems that are only being currently covered in my tutorial series. The Neo Geo has something called a fixed bitmap, not a raw bitmap. Well, there's two. The Neo Geo has a very special format of ROM data for its screen, and I'm using the fixed layer in my tutorials, not the sprite layer, and the fixed layer and the sprite layer use different formats, so possibly later I'll have a save sprite bit, raw sprite bitmap or something option for that other thing, but as you can see, I'm really covering a lot of systems in my tutorials next year, and I've not created these in advance. I've actually got the tutorials ready to view the result of all these export options, so I can export this file into all of these systems and view it right now because I have the code ready. I've already done it for my Chibico sprite. So you can see that it supports to a basic level a lot of systems, but I have no intention of stopping developing this program. So long as I'm programming Z80 games or 6502 games, 68000 games, I'm going to be working on this. The whole point really of doing the programming on these retro systems was to try and improve my own experience and skill and things. I'm not going to use someone else's programming if I can write my own, even if my own is inferior. So I'm going to keep working on this and adding everything I want to do with it within my limitations. So it's only going to get more powerful, especially with these 6502 and 68000 systems. So hopefully there's a lot to look forward to with regards to this program. Those are the export options. We also have the sprite list, which is just a summary of the sprites in total, and I've completely wrecked these. But oh no, it's just because I've got it set to I thought I completely wrecked the entire sprite list. I thought it was quite clever, but it's just because the viewing mode was set wrong. So we got the sprite list here for just quickly browsing around. Sprite data offset. This is related to byte alignment. Now, it's currently offset hexadecimal 180 bytes, 384 bytes maybe. Now, the header contains the information of the sprite sizes and things, and the actual sprite data starts later on, and that's essentially the size of the header. Now, In some cases, you will want this to be set to 256 bytes. You'll see there's an AMD symbol there. It's the same as the Amstrad CPC and means hexadecimal. So sometimes you will want it to be, the header to be 256 bytes, which will limit you to, I think it's 28 or 48 or something, sprites, which is enough for the tiles. But the tiles do need the first sprite to be on aligned to a byte origin. So that is useful in some special cases. And then you've got notes here, and this is a free text box, and I'm using this to store information about the files. There's none in that one, but maybe. Yes, here you go. This is the level sprite and tile file for the MSX, saved to blah blah blah, using blah blah blah. So this is telling you how to actually work with the file. It's a notes field, and what I'm planning to do is make all of the files that the Chibiakumas new game, Chibiako versus the Coding Bugs or whatever it's called, is going to have these comments on all the files that it uses so that you can open them and change them and then know what you need to do to get your new sprites back into the game. I'll just explain. This Chibiako versus the Coding Bugs game, it's like a spoof game. It's not, I mean, it's going to be a game. You're going to be able to play it. Maybe you'll enjoy it. But it's not, I'm not creating it because I think this is a good idea for a game or the plot makes any sense. It's a tutorial that you can play. And I'm going to teach you how to change it so that you can take the game, put your own sprites into it and reconfigure it into something of your own. So this notes field was added purely for that purpose, so that if you've got a sprite file, you've changed it and you think, well, what do I do with it now? Well, here's where you need to save it. Here's the option you need to use to save it. And in a lot of cases, it will tell you if you need to rebuild an assembly file to finish the work, because sometimes they're embedded into assembly files, the sprite data. It'll tell you that as well. Okay, so that ended up a bit of a longer description of the program than I expected, but never mind. So that's how the program works at some level. But what about the files it actually exports? Now, as I've said, Chibiakumas uses a binary sprite format, and it has header information because the sprite viewer is fairly advanced with what it can do, and it does it all automatically to an extent. So we just tell it what sprite number we want to show, and it knows what size that sprite is and does the transparency if required. So it's got to have a header that stores that information. And the header is slightly different on the Spectrum and the MSX and the Amstrad CPC. So the Spectrum and the Amstrad CPC are relatively similar. So here's the layout of the header, and the start of the byte data is shown here. This is the actual sprites here, and as I said before, the start is actually defined by that offset that we can configure. Now this file has been set to a 100 offset here, so it starts to the binary data of the sprites starts 256 pixels in, and you can see there's a lot of blank data here, so we've wasted a little bit of memory there, but never mind. So each sprite is represented by 6 bytes, so sprite 2 would start here, and sprite 3 would start 12 in. Actually saying that, the sprites are numbered from 0, but anyway. So the first byte is the height of the sprite, so you can see this one is 16 pixels wide, and the second byte is the width in bytes, so this one is 8 bytes wide. The next byte is the Y offset. Now I said before, if lines of the sprite are blank, then they're actually skipped from the export to save memory. Your sprite in theory may be 16 pixels tall, but maybe only 10 of those pixels are in use, and there's 3 blank lines at the top and 3 blank lines at the bottom. In this case, it would save the sprite height as 10 and the offset as 3, because it needs to move down 3 lines before it starts drawing the 10 real lines. And again, this is just to save memory. So in this case, that's not being used. This sprite is fixed size, and this is because it's tiles. Tiles have to be fixed in size because the drawing code actually fills the background with them. So there's no messing around there. It's not actually a sprite viewer that's using this file in the end. To be honest, the header isn't even used at all. So that's the offset, Y offset, before the sprite is drawn. Now this was going to be the X offset, and it's actually named that in the code in some pages. It's never used as an X offset. There is no X offset, it's used as the settings. So in some cases, sprites can be set as transparent, and they use an advanced piece of code to draw them, or they can be p-set, which means they wipe out the background and have a black background around them and delete anything behind them, which are much faster. So as well as that, I said before that certain byte configurations, like colors 0, 1, 2, 3, may be the transparent byte, so to speak. And again, there are various options with regards to that. Sometimes if all the pixels are 0, it's transparent. If all the pixels are 1, it's transparent. If the pixels are 0, 1, 2, 3, it's transparent. And that is also used by this configuration byte. On the Spectrum, it's also used for how the background colors are used. If the sprite has no background color, and this was used for the water level because the water shows through the Chibiako sprite, that can be done here, but again, it does slow things down a little bit in some cases. So that's the settings byte, and then these 2 bytes are the offset. So Sprite 0 starts at offset 0, 1, 0, 0, because this is little endian. So that means that Sprite 1 starts here. And then this will repeat onwards and so forth. So you can see here the Sprite 1, the second sprite, is at 0180, which would be off the file export here. So those 6 bytes are used for every one of the sprites, and when all the sprites are done, there's a blank piece of space, and then there's the sprite data. So we can use the header, and we do, to find the sprite data, and then we just view the sprite data on screen, and we know the size of the sprite from these bytes here. That's how it works on the Amstrad CPC on the Spectrum. Now the Spectrum, once you've done the bitmap data, which is of course black and white, there's then a bank of color information of the same sprite as the size of the sprite. Now I'd strongly recommend you do the sprites as 8x8. They certainly need to be a multiple of 8 pixels wide, but generally speaking it works best if they're a multiple of 8 pixels tall as well, because otherwise you start to have problems with the color information. But it can support ones that aren't, but I found it worked very poorly, so I don't use it. It's up to you if you want to try. Now that's how the Enterprise, the Sam Coupe, the Spectrum and the CPC work. Unfortunately the MSX cannot work in that format. As I've said before, the MSX does not have its graphical data in the Z80 memory. It has it in the VDP memory, and it essentially copies areas of the screen from one part of the VDP memory to another. And so what we do on that system is we still have a header, but our byte data is saved in a completely separate file. And our header is actually more complex. Rather than 6 bytes per sprite, we're actually using 10. Okay, well let's have a look. Well, the first byte is the same. It's the height of the sprite. The second one is the width. Then we have a Y offset again. Now again we have a settings byte. Again, all very similar to the original one, but this is where things get different. Now the next byte is the X position. It's coloured in wrong here. This should be in pink. The next word is the X position of the sprite. So this one appears at the top left-hand corner of the sprite data, which won't be the same thing as the top left corner of VDP memory. We do have to offset it later, but and then this is the Y position. So again, this is in the top left-hand corner, this X and Y coordinate. And then here we've got the width. Now the width it's saying is 0, but what it actually means is the width is 256 because it's rolled over. 256 is of course the limit, and then the Y height is 16 pixels. Okay, well, as I've said, the data is stored in a second run length encoded file. When you actually export a file, it saves what it saved into that ILE file into the clipboard, just in case you want to check it out, make sure everything looks okay. And what I've done is I've saved it here. So here are the sprites in this file. Now you can see this is the backgrounds here for the Tragical Chase game. These are the sidebars for the vertical levels, and here are the enemy sprites here. So you can see here, I said this sprite here is 0, 0, so in the top corner. So it looks like it's these clouds. It's 256 pixels wide, which makes sense because this is the entire width of the VDP memory, which is 256 pixels, and it's 16 pixels tall. And so you can see it goes down up until you've got these kind of buildings here. So that's the first sprite, and you could look along, and if I could be bothered to work it out, you'd see the next sprite start 16 pixels down, 0 across, and it's again 256 pixels wide and 16 pixels tall, but the next one's only going to be 8 pixels wide, and then when you get to these, they'll be much further down and they'll be much narrower. So basically it's almost the same format, but I added some extra data because of rather than trying to calculate things, it was easier just to have this data is basically dumped into a VDP command and then executed. So it's all about making it work well with the MSX, which can't do that bitmap format. Now I may or may not, I haven't really worked it out yet, convert these for all the other systems. As I say, I want to create games including systems like the Game Boy, and unfortunately obviously different systems have very different limitations with regards to sprites, and some have hardware sprites but they can only view 8 hardware sprites, and other systems have 64 hardware sprites, and other systems have no hardware sprites, and I haven't really worked out what's going to be best to do going forwards with regards to doing sprites on a lot of systems. Do I use software sprites only? Do I use partially hardware and partially software? So I don't know, but as I say, these formats can be used on the MSX, the Spectrum, the CPC, the Enterprise, and although I never used it, the code does work on the Sam Coupe. Okay, well, I was going to do some more stuff and actually draw some sprites today, but this has gone on quite long enough, and I'm sure practically everyone has switched off already. So I will do a part 2 where I actually draw a sprite. Thanks for watching today. I hope you've enjoyed it. You can download the Sprite Editor today if you want to and have a play with it yourself. Thanks for watching and goodbye.